this is actually a repeat of information that I gave last week at the Chesapeake Community Modeling Symposium, focusing on a project that we have going on over on the Eastern Shore in the town of Queenstown. This is a project funded by NOAA through SciSeat. It's a $250,000 project where we're using multiple models, evaluating the use of multiple models to inform land planning at the local scale. And today, what I'll do is I'll start off by providing some background and context for the project, and then put that into the framework of the overall decision-making framework that we used at the planning scale. So I have to tell you here that I'm wearing both hats, both as a watershed planner and also a watershed modeler. So I'm going to move back and forth between those two roles. And then I'm going to finish up with really kind of highlighting what I think is significant from a scientific standpoint and moving forward with managing the Chesapeake Bay watershed and reducing non-point source pollution. So the reason that we're focusing on the local scale is because almost 90% of the watershed and its shoreline is rural. And so this is the scale at which local planning is being implemented, where most of the land management plans or decisions are being made. So we really need to understand the connections between the science and the management at this scale. I focused on Queenstown not only because I live there, but also because it's one of these municipalities where sewer and water infrastructure have really limited growth over the past 10 years. And it's close enough to Baltimore and Washington, D.C. that it's really primed for growth over the next 30 to 50 years. In fact, Maryland State and in the Chesapeake Bay program think that this area could grow by as much as 20 to 30% over the next 30 years. So it's about 20 minutes east of Annapolis, 10 miles east of the Bay Bridge. So it's very close to D.C. and Baltimore. The town is in the process of developing its comprehensive plan, and one of the main priorities of the community is to preserve open space around the town and preserve the town's rural character. So what the Planning Commission came up with was the idea of accepting growth, consolidating that growth at a higher density closer to the existing municipality, and in return preserving the open space in the surrounding town planning area. Now, to accomplish this, we need to appease the landowners and assure them that they're going to get the full value of their land. And we also have to convince the citizens to accept the additional growth and the expansion of high-density housing around the existing municipality. So what the Planning Commission did was came up with two different growth scenarios. One is a distributed growth scenario. Let me back up a second and point out that the top diagram highlights the existing municipality in red. The second middle diagram would represent full build-out under county zoning. So you can see the difference in development area between the county distributed growth and the current growth scenario. And then the second growth scenario would be the consolidated growth option. Again, where we have a relatively high density of development occurring adjacent to the existing municipality, and we manage or we have say over what's occurring in the outlying areas, especially in terms of agricultural practices. And you can see here the difference in development, agriculture, and forest area. We can see that development almost doubles under the distributed growth scenario and remains largely unchanged, only a 3 to 5% increase in development area under the consolidated growth option. So back to wearing my planning hat, in addition to assessing non-point source pollution, we also wanted to look at open space and wetland and forest protection. But we also needed to consider other factors like traffic impacts, water and sewer infrastructure, school population impacts, job creation, and local economy. And these are all equally important to protecting the environment and preserving the character of the town. I just wanted to take the opportunity to also highlight that under a recent bill passed by the state, the Maryland House Bill 1141, the towns are required to prepare a water resource element. And this, I think, is a really great opportunity to intersect watershed science with local planning, because it requires the towns not only to assess sewer and water infrastructure impacts, but to do these non-point source assessments. We wanted to use multiple models in part because of other work that we're doing at CERC, looking at comparing different watershed models. And this is actually the third project where we're using multiple models to assess watershed impacts. And this is a highlight from one of our studies looking at published models in the Patuxent watershed. You can see here there's an excerpt looking at annual average total phosphorus loads in 3 subbasins of the Patuxent watershed. We have Laurel, West Branch, and Bowie. And the different colors represent different models, including the Maryland Department of Planning's non-point source assessment model, CERC's empirical and landscape models, the Sparrow set of models from 87, 92, and 97, the Chesapeake Bay's Phase 4 and 5 model outputs, and also the Patuxent landscape model. And what I want you to realize or notice is that if you look at any one color, you'll see that most often a model does really well at one location, but relatively poorly at another location. So for example, we can look at the Sparrow 97 model. You see it does a really nice job of predicting total phosphorus loads at Laurel, but a relatively poor job predicting phosphorus loads at Bowie. So this really convinced us of the value of using multiple models. It provides a formal framework for accounting for the structural uncertainty of the models. And it also provides a stronger basis or more coherent basis for communicating the uncertainty to the land managers. Okay, so for our Queenstown application, we used preliminary output from the Phase 5 model. And we used the Maryland Department of Planning's and Environment's non-point source assessment model, which is essentially a downscaling algorithm for applying the Bay program's data. We also developed a SWOT application, soil water and assessment tool, and also used the generalized watershed loading function, both developed independently. And then finally, we used the long-term hydrologic impact assessment model, which predicts annual average loads. And this is a fairly popular model with the planning community, which is why we also included it in this analysis. For the temporally dynamic models, including SWOT and GWLF, what we did is we calibrated the models with 3 basins, including Greensboro, and 2 smaller basins where the Smithsonian has collected monitoring data. And then we used Ruthsburg and 2 additional watersheds to validate our models. And then we could transfer the parameters used from that calibration to look at land cover impacts in our target or applications area. For application area, what we did is we used 2-meter DEMs to delineate the watersheds. And then we intersected these hydrologic units with the planning area so that we ended up with hydrologic units that we could use to communicate between the watershed models and the land planning scenarios. And this is just an overview of the model that we used for the calibration and validation. You can see here, the time period for which we have observation data ranging from 2 to 20 years. For the model applications, we used 10-meter DEMs, 2,000 land cover data from RESAC, and the Surgo soil database. So the first set of results that I'm going to share with you are derived from the Maryland Department of Planning's non-point source assessment. And you can see I have total nitrogen on the left and total annual average total phosphorus loads on the right, with the current or baseline conditions in the top panel, the county or distributed growth conditions in the middle panel, and the consolidated growth impacts on the bottom panel. And 2 points to recognize. First, relatively high total nitrogen and total phosphorus loads. And this is the class breakout here is based on what Sparrow's been using to communicate their results. So these nutrient loads are on the higher end of the nutrient loads predicted by the Sparrow model. The second pattern, or that you probably realize, is that there's not a lot of difference between the 3 scenarios when you're looking at either total nitrogen or total phosphorus. And this will become even more clear as we look at the tabular data. So what we have here, total nitrogen inputs on the top, outputs, to the lower Chester River, and on the bottom we're looking at outputs to the upper Wye River. I should have pointed out that Queenstown straddles both of these watersheds. And then what we're looking at is the total discharge of nitrogen predicted for our different build-out scenarios. Current county-zoned build-out, consolidated growth with no agricultural BMPs, and the consolidated growth with agricultural BMPs. And if you look for any single model, you see that there's not a lot of difference in the total nitrogen loads predicted in either watershed. And this becomes really clear when you compare predictions for any single scenario among the different models. And clearly, the range of variation in the predictions among the models is much greater than the range of variation imposed by the different land cover scenarios. And the same pattern emerges when we look at total phosphorus loads for the lower Chester River and upper Wye River. Again, we get relatively small variation among the different land cover scenarios in comparison to the variation predicted from using multiple models. So when we bring this back into the decision-making framework, right, and think about what are these watershed impacts for the different alternatives that the Planning Commission is considering, what ends up happening is because there's relatively small differences among these different scenarios, these objectives really fall out of the decision-making framework. And these other considerations play a much bigger role in evaluating which alternative to consider. And what's really hard or what really kills me is when you think about the complexity, the time, and the resources that went into developing these predictions in comparison to the tools that are being used to evaluate the alternatives for these other considerations. In some cases, it's just a simple ranking of what we think is going to have the most impact versus the smaller impact. So coming back, putting back my science hat on, we remain convinced that using multiple models is a really effective way for understanding the uncertainty in the model predictions. And I think by what we've done by using multiple models is we've improved our understanding of where the uncertainty in the models lies. And we get concrete ideas of where to move forward, where to target research, how to interpret the model results from using these combination of models together. The second point that I wanted to make is that I think our results and our effort shows that these downscaling tools that the state is using is really ideal for this level of planning, right? So clearly, investing in the development of a complex model for the local scale is probably not the best use of our resources. Maybe the way we can move forward is to think about using multiple models to come up with a probable range of loading coefficients for different land covers and best management practices. Those are the two main points. The third point that I wanted to put on the table as my experience is that it's been really interesting to realize that the citizens and the Planning Commission largely think of agriculture and open space as equal. And we all know that that's not true, and something that we should think about how to address. And so with that, I'll end there.